All right, so I wanted to look at exponential growth and decay and basically the function that represents exponential growth and decay and how it can be growth and how it can be decay and what all these symbols mean. So when I think about exponential growth and decay, basically governed by this function, and there's a lot of things obviously unknown here, but I'll explain what each are. So basically we say P equals P naught times e to the power of kx. Okay, that P naught there is your initial quantity. And sometimes when we talk about exponential growth, sometimes we're talking about populations of things. So I've just chosen P as my letter. So P naught would be whatever your initial population starts out at. We're talking about growth. Uh, K is our growth slash decay factor. So this will determine whether our curve is growing or whether it's decaying as X, which is time passed since the very start, increases. So depending on whether K is positive or negative, we're going to get growth or decay. And obviously the other thing that's in there is just a number, which is E, which is just 2.71. So yeah, hopefully familiar with that. So this formula, before we sort of try a problem, let's just see if we can make some sense of it in terms of a graph. So if we look here, we've just got the formula here. We've got sliders for P naught and K. So you notice as we change the P naught value, that's just changing our initial value. So if we look here, that P naught value tells us what is the initial starting population, because that's when X is 0. And remember, X is time. So if I made P7, my population of rabbits or whatever it might be starts out at 7 when time is 0. Okay, so yeah, that P naught value tells us, yeah, whatever value we start at. And then our K value basically tells us our growth rate. So if K is larger, um, the rate of increase is larger. So you can think about it in terms of the gradient. The gradient would be larger. So your rabbit population or whatever it is growing more quickly if K is larger. The interesting thing though, as we said, is K can be negative. So you'll notice it sort of flattens out as K gets close to 0. And then it becomes exponential decay. So we get a situation like this. So this is when you have things like radioactive decay, or maybe some bacteria is being killed off. And so the bacteria starts at some amount and it slowly dies as the antibiotics kick in. So you get graphs that kind of look like that. So what we can do is we can try an example of this to see what sorts of questions we can answer with this knowledge. So the question might be something like the population of a town was 8,000 at the beginning of 2007 and 15,000 at the end of 2014. Assume that the growth is exponential. So you can see, when we talk about growth, we're talking about a very specific kind of growth. It has to obey this function in order for it to be exponential growth. So then the two questions we might be able to answer is find the population at the end of 2016, and then in what year will the population be double that of 2014? So two slightly different questions. Let's see if we can tackle them together. So the first thing we don't know is we don't know what K is. So we need to find out what K is, and we've been given some information in the question that we're going to use to find K. So we do know that when X is 8, now let's have a think where I got 8 from. So in 2007, at the start of 2007, and at the end of 2014. So 2007, 2008, 2009, 2010, 2011, 12, 13, 14. So that's 8 full years that have passed. So when X is 8, we know that the population is 15,000. So after 8 years, the population is 15,000. And we know that P naught is 8,000 because in 2007, at the time we're starting, we had a population of 8,000. So what we can say so far about our function is, yeah, we can sub these things in. We know that P is 15,000 equals 8,000 times e to the 8k. And what we can do is we can solve that on our calculator to find k. So we're going to solve 15,000 equals 8,000 multiplied by e to the 8k. In respect for, I think it'll just, if I do that, it'll solve for k. No solution. Um, Let me try that again. I take that interactive, advanced, solve for K. There we go. So we get that. Let's put it as standard. Okay, so we get this messy answer. We put it as a decimal. It won't give it as a decimal for some reason. That is just a number, so I'm not sure why it's not giving me that as a decimal. Okay, so I'm not sure what's going on with the calculator here, but it's a bit of an odd answer. Which you can see on the denominator is log base e, or the natural log of e. Now, the natural log of e is just 1. So yeah, this is in decimal form. I'm just not sure why they've put it over log base e. But basically the answer is just, yeah, whatever the numerator is, because we're dividing by 1. So 0.0785. So if we come back to here, we can say, if you work it out by hand, you'll get this, k equals 1/8 log e of 15 on 8, which is, yeah, approximately 0.079. So when you're doing these types of problems, make sure that you take the specific value from the calculator and you don't do any rounding. So yeah, with that information, we know what K is, and so now we can find the population at the end of 2016. So let's see if we can do that, because we know this is our rule, approximately, with K being approximated to 0.079. We substitute in at the end of 2016. So that's going to be X being 10, because again, all of 2007 counts as the first year, and then till the end of 2016. So that's actually 10 years. And then you get an answer of approximately 17,550. So again, you chuck that in your calculator and you'll get that as your answer. So in what year will the population be double that of 2014? Well, in 2014, the population was 15,000. So we need to know when the population is 30,000. So we're going to let the left-hand side equal 30,000 and set that equal to our function, 8,000 times e to the 0.079x. Put that in your calculator, you get 16.82. So in the middle of the 16th year, you'll get a population of 30,000. So that's going to be, I'll let you work it out, but it's during the year 2023 in this case. Okay, and then obviously we've got our axes scaled here. So the grand reveal, there's our curve. That's what it looks like. You can sort of see that this this y-intercept here is at 8,000. So, and then it just, yeah, grows exponentially from there. Let's just look at the graph in a bit more detail. So if we go over here, we can actually see the graph in more detail. We can see some of these points. So yeah, that's at 8,000. We said that after 10 years, it'll be 17,550. So let's find that. So yeah, close enough. Again, that's just going to be a rounding situation there, but yeah, so you can see how this curve sort of works, and this is a classic example of exponential growth. So hopefully that explains what exponential growth is, and hopefully you can see as well where exponential decay might come in. Yeah, if something was decaying, basically our k value is going to be negative. So if we made that negative for whatever reason, we're doing a different problem, we'd be decaying from 8,000. Because it's a reflection in the y-axis is another way to think about it. Anyway, hopefully that's helpful. Good luck with your studying at the moment.